Hello, everyone. Thank you for attending the BAS Electrochemical Webinar 2024 Spring. Today, it will be the BAS's 22nd webinar, and Professor Masa-aki Haga from Chuo University 11th lecture, series of lectures in the field of coordination chemistry and electrochemistry, introducing basic electrochemical methods and applications with a focus on organic complexes. Today's theme is coordination chemistry and electrochemistry, electrochemical quartz crystal microbalance, fundamentals and applications.
Hello again, this is Masa-aki Haga. This seminar series is now in its 10th presentation, and today I'd like to present the basics of electrochemical quartz crystal microbalance, its measurements and analysis, and some examples are shown as a case studies. I have previously described spectroelectrochemistry, which is a combination of electrochemical method and spectroscopic method, such as infrared spectra and UV spectra. Here, I discuss an analytical method that combines quartz crystals and electrochemistry to detect mass change associated with electrochemical reaction on the electrode. In the quartz crystal microbalance, gold electrodes are deposited on the top and bottom of the thin quartz crystal plate, as shown in here. The AC voltage is applied externally to the electrode. The frequency at which the quartz seed resonated is measured by frequency counters. The resonance frequency change when analyzed is observed on the electrode. By detecting this change in frequency, information on the mass change on the electrode surface can be obtained. By connecting the gold electrode on the quartz seed to a potentiostat, the mass change on the electrode can be measured as a function of potentials. This technique is called electrochemical quartz crystal microbalance, as shows EQCM as short. First of all, I would like to discuss the principle of how the use of quartz crystals allow us to determine the mass change. Before going further, I would like to show you the future of quartz crystals. Here is the crystal structures of quartz and photograph of naturally occurring quartz crystals. In the crystals, the tetragonal SiO unit, as shown in blue colors, are connected with SiO-Si bond network. Crystallographically, quartz crystals belong to the trigonal systems and point group symmetry 32 or D32 in Hermann-Morgan notation system, and threefold improper rotation axis and twofold axis of symmetry. From the axis, the SiO-SiO bonding consists of polarized helix linkage. Therefore, the quartz crystals have optically active right-handed and left-handed crystal present. This polarized helix structures is the origin of piezo effect. However, this alpha form is converted to hexagonal beta quartz at 573 centigrade by phase transition. The beta quartz has no piezoelectricity, which is a sharp contrast to the alpha form. Quartz crystal units have zero temperature coefficient over broad temperature range and therefore have excellent frequency temperature characteristic. Moreover, quartz crystal units are extremely stable both physically and chemically. Therefore, frequency change after aging is extremely small. Piezo effect in quartz was founded in 1880 by Pierre Curie with Marie Curie's husband and his elder brother Jacques Curie. They found that by applying pressure on the quartz crystals, polarization occurred, and conversely, applying voltage to quartz crystal was deformed. Further, when an alternating current is applied, the crystal oscillated at a certain frequency. Actually, quartz crystal units have various vibration modes depending on the crystalline phase and cutting orientation. Here is shows several cutting directions, which are called as AD, BD, CD, IT cut, etc. AD cut is the most well-known cutting orientation, which crystal phase is cutting at 35 degrees with respect to the crystallographic x-axis. As for frequency, the parameter to determine frequency is different depending on the vibration mode. For example, the frequency of thickness shear mode resonator, AD cut or BT cut, tuning fork type quartz crystal resonators is decided by quartz thickness, the lengths, and widths. Each vibration mode have a different frequency range and electrical performance, and therefore appropriate vibration mode should be used depending on the module. Owing to this excellent frequency stability, quartz crystal units are used for communication devices such as cell phone and wireless applications, as well as consumer devices such as televisions, video recorders, digital cameras, and computers to provide accurate reference signal for processing a huge volume of information simultaneously and quickly. Moreover, quartz crystals units are widely used as the source of standard clock for wristwatch. At first, what happens in the quartz crystals when external field applied to the quartz crystal face? Deformation of the crystal lattice due to external force produce lattice deformation, which induce the polarizations. Here shows two different crystal phase directions between two electrodes. When the alternating voltage is applied from the vertical directions with respect to the x-axis, the contraction expansion mode vibration occurred. On the other hand, when a AC voltage applied to the axis of AD cut with inclined x-axis, the sliding force act in an opposite direction at the top and bottoms, which lead to the shear lattice vibration mode. Depending on direction of crystal lattice plane to external force, different lattice deformations are produced. In the case of eddy-cut quartz crystals, the electric field provides the horizontal thickness shear vibration, which is applied for the EQCM quartz crystal microbalance devices. Let's consider the eddy-cut quartz crystal shear vibration mode. The transverse shear force generated when the AC voltage applied to eddy-cut quartz causes acoustic waves with back and forth motion in quartz film. The frequency F0 is the resonance frequency, which is calculated by dividing the speed of sound wave propagations by quartz film thickness, as in these equations. This oscillation motion can be thought of a system analogous to spring or pendulum vibration. In the case of pendulum vibrations, energy dissipates over time and frequency change, but in the case of quartz, energy loss is very small, so the exact frequency is maintained, which is useful in various applications such as clock frequency. In addition to the frequency, in the case of quartz, when the substrate is absorbed on the quartz surface, the thickness changed, and therefore frequency changed. Savory equation is established between the frequency change and the mass change of substrate, in which quartz density and shear modulus are included in these equations. Although overtone also occurs in acoustic wave in quartz, the fundamental waves is usually used. The resonance can be stimulated at higher frequency, which correspond to the odd number overtone or harmonics. So, our 5 MHz crystals also have overtone at 15 MHz and 25 MHz and 35 MHz, etc. As the speed of the acoustic wave in quartz is essentially fixed, the surface displacement is reduced for each successive overtone. This means the different overtone can provide different information about the film on the sensor surface. Here is a summary of the history of development of the quartz crystal microbalance. Since the discovery of the piezoelectric effect in quartz by Curie brothers in 1880, a quantitative formulation was proposed by Solvay in 1959, which shows the resonance frequency varied in proportional to the mass of the substance absorbed on the quartz surface. In the beginning, the Solvay equation is applicable only for the hard, rigid, uniform thin film on the quartz. In 1985, it became clear the viscosity and density of the solution can describe the frequency shift even when the EQCM is in contact with the solution, liquid solutions. In 2009, Quartz crystal microbalance with dissipation monitoring (QCMD) instrument becoming commercially available, allowing the viscoelasticity of solid and membrane and liquid to be monitored in terms of frequency energy decay change, allowing the observation of change on the soft matter on the surface. This figure shows the quartz crystal sensor is resonated at the fundamental and third orbital frequency, and complex impedance spectra for conductance as blue line and susceptance as brown line versus frequency is shown right-hand side. From impedance analysis, the resonance frequency, which is the frequency of the conductance maximum, and the bandwidths of the peak are determined. Quartz crystals are electric-mechanical device, so the mechanical vibration can be described by the electrical equivalent. Quartz resonator can be described as LCR circuit as shown in this figure. In this system, our electric circuit has an inductor L, capacitor C, and resistor R connected in series. The static capacitor C0 is placed in parallel. The well-known tank circuit in AC circuit is a good representation of how the QCM works in a circuit. When the switch 2 in tank circuit is open, the capacitor is charged, but when the switch is closed, the capacitor discharged through the inductors and the current drops to zero. The inductor L1 represents the mass displaced during the oscillation. The energy stored in C1 during the oscillation, and the energy dissipation due to loss in resistor R. The displacement of quartz crystals is equivalent to the capacitor charging in the LCR tank circuit. When the quartz crystals are immersed in a liquid, the new component related to the liquid mass as L2 and viscosity component R2 arising from contact between the quartz and liquid should be considered. Vibrational dissipation become more important factors. When the quartz resonator is used in liquid, the liquid density and viscosity changed the resonator characteristic. This liquid viscosity provides additional energy damping. Therefore, the previous electric circuit additional inductance L2 and resistance R2 are added. The vibration of quartz crystal parallel to the QCM liquid interface result in the radiation of shear waves into the liquid. This shear wave velocity decay as exponentially damped cosine function according to the equation 1. The decay length is given by equation 2. This leads to the equation 3, which gives the dependence of the resonant frequency on liquid with density and viscosity. The shear wave velocity decays in liquid because of velocity gradient along the Z direction normal to the surface. The Soberray equation was originally founded to be varied for in the gas phase, but later the equation can be also applied for the mass change on the rigid flat film immersed in liquid. This finding opened the way for the broad application of EQCM in electroanalytical and biological chemistry, environmental science, and sensor applications. In recent years, EQCM technique extended to measure not only the mass change by the resonance frequency change, but also analyzing the impedance analysis on resonance frequency change with dissipation by surface viscoelastic interactions. From the impedance analysis, two parameters, the peak of resonance frequency and full width at the half height of the resonance peak, provide the important information for the surface structures. Three different cases are shown in conductance versus frequency plot and temporal change of resonance frequency. At first case, when a thin rigid layer film is formed to the one side of a QCM electrode surface, the increased mass lead to the drop of the resonance frequency without no peak width change. As the second example, when the quartz crystals is immersed in viscous liquid, if the viscoelastic film is deposited on the QCM sensor surface from solution, the negative shift of resonance frequency and also the increase of peak width. Temporal curve shows the frequency of peak width becoming increased with the time. The third example is the viscoelastic layer is deposited on the sensor surface, particularly in non-Newtonian fluid. Both resonance frequency and peak width are changed in this figure. For these films, the frequency response due to the added mass is reduced as some of the vibration waves is dissipated with the film because of the soft film is attached. Therefore, small resonance frequency shift was observed. Considering the dissipation effect, the dissipation factors D is defined as in these equations as the ratio of the width of the half height of the resonance peak to resonance frequency as shown in this equation, which is inverse of the quality factor Q. Q is the measure on damping or loss of energy in resonance system. Other method to characterize surface structures on EQCM, ring-down method is known. In this method, decay of the oscillation is measured by applied voltage on EQCM chip. In viscoelastic film, the dissipation occurred, therefore the oscillation decayed quickly. Therefore, the effect of the loss of rigidity on QCM are also observed as the frequency peak change or decay. For measuring the electrochemical quartz crystal microbalance, EQCM, the QCM chip is mounted to the bottom of the glass cylinder cell. The quartz crystal commonly about 5-meter diameter with excitation electrode on the top, such as gold, platinum, or even ITO vacuum deposit on the top. One side of the excitation electrode is facing the solution, the opposite electrode facing air. The isolation of opposite electrode is important to get the stable frequency response. This photo is commercially available EQCM chip holders. The EQCM chip is fixed by holders, and the front side and back side is concealed by the cover. In the photo, backside cover is removed. QCM electrodes are electrically connected to the oscillators and frequency counters. The excitation electrodes such as gold or platinum is also connected electrochemical analyzers, such as potentiostatic experiment, and set in the conventional counter and reference electrode system as shown in this slide. From several equations, we can calculate the mass change. For 5 MHz QCM chip, the sensitivity factor is 56.6 Hz square centimeters per microgram, so 1 Hz change corresponds to 17.7 nanogram per square centimeters mass change. For EQCMD measurement, the frequency counter is replaced the network or impedance analyzers. Recently, QCM equipment is commercially available that can measure the frequency response of admittance, conductance, and susceptance. Now, I show you several case studies for EQCM. The first example is the gold dissolution and deposition in ionic liquid. The polycrystalline gold-coated quartz crystal electrode in a room temperature ionic liquid of 1-ethyl-3-methylimidazolinium tetrafluoroborate, EMI-VF4 as showed no electrochemical response. However, when the EMI chloride is added in EMI-BF4, the CV and EQCM response was observed as shown here. This CV peak at 0.25 volt versus AU wires allows from the electrochemical oxidation of AU surface to form AU1Cl complex, which is very stable and reversible bottomogram response of AU1, AU0 coupled. In situ EQCM technique combined with CV showed cathodic deposition of A1 gold ion to AU metals, and cycling of the potential provide the anodic dissolution of gold from the gold electrode surface and deposition on the QCM chip. The frequency change of quartz crystal electrode during the electrolysis can be interpreted in terms of rigid mass change. The CB of Prussian blue modified electrode has been reported by Etaya at Tohoku University in 1982, in which Prussian blue nanocrystals are deposited on ITO electrode by electrode deposition. Two reversible waves are observed in the cyclic botaniograms as shown here with black line. In this redox process, it is known the metal ions such as potassium ions are taken into the vacancy of Prussian blue nanopore, and their release is accompanied by oxidation or reductions. Therefore, a thin Prussian blue film was electrode deposited on a QCM chip on an ITO electrode on a quartz crystal surface and measured the EQCM response. The EQCM response is shown in the red and blue line. When the potential is swept to the positive directions, Prussian white, which is a fully reduced form, is oxidized Prussian blue, resulting in an increase in resonance frequency, that is, decrease in mass. A further sweep of the potentials toward the positive direction, resulting in oxidation from Prussian blue to beryllium green, which loss of the mass is observed. This indicates the uptake and release of potassium ion into the Prussian blue structures can be clearly observed at the EQCM. Next, a pulse potential sequence was applied to a modified Prussian blue nanocrystal on the ITO QCM chip. At the start at 0.5 volt, the film is Prussian blue state. But when pulse applied to plus 1.2 volt, a negative mass decrease response on the EQCM was observed. The minus 0.2 volt pulse show an increase in the mass response, indicating the ion incorporated into the Prussian blue nanopore occurred very quickly. Even the successive pulse sequence, very stable and reproducible response was observed. This Prussian blue EQCM behavior is presented in these papers. The third example is the film of polyvinyl ferrocene at the gold electrode on the QCM crystals. Here shows the effect of the anion upon the oxidations. Curve A on the bottom is the CB, and curve B on the top present the EQCM frequency response. Upon oxidation of PBFC ferrocene, the QCM frequency decreased, indicating the increase of the mass. This results in incorporation of counter-anion captured into the PBFC plus as shown in these equations. Upon scan reverse directions, reduction of PCFC film occurred and the frequency increased back to the original values. The frequency change, that is, mass change, were linearly correlated with the charge passing during redox process. This indicates redox process did not cause any solvent incorporation into the film. Only anion incorporation is important. The EQCM response are strongly dependent on the kind of anions. In the case of chloride, the oxidation induced the detachment on the PBFC from the electrode. Ruthenium complex with 2-tridentate bis-pyridyl bis-bendoimidazole pyridine ligand form a multi-layered coordination network structures in which pyridine groups in the side chain produce a polar structures by the coordination of palladium-2 ion on the QCM electrode. Upon ruthenium-2 to ruthenium-3 oxidation, this film captures PF6 anion from the solution for charge compensations. A decrease in the resonance frequency is observed, and calculation shows the amount of charge corresponds to the number of anion captured. The EQCM response also shows the process is reversible when the potential is received to the reducing negative side, releasing ions. Today, I talk about the principle of EQCM, measurements, and analysis method. In summary, there are three main points. The Sauber equation is the equation that expresses the relationship between the resonance frequency change between two electrodes and absorbed mass change. Initially, this equation was only applicable to absorbance on the rigid solid surface and gas phase, but it was found that this equation can also be applicable for liquid QCM contact system. In the case of liquid, energy dissipation occurred, and it is now known this dissipation can be applied to the soft biomembrane and other material based on impedance analysis of frequency dependence of admittance as the EQCMD method. As a result, the application of EQCM and EQCMD is expanded to obtain information on the in situ surface structures and change of state when electric potential is applied on the surface. Here is a reference for today's EQCM. The number 5 is the original paper for Sauber formulated the relationship between resonance frequency change and mass change. The last three references deal with EQCMD studied applied to the energy storage electrode, such as lithium manganese oxide layer materials or alkaline anion exchange membrane materials for fuel cell. During the anion exchange, the membrane swelling occurred on the electrode, which can be monitored by impedance analysis. If you are interested in these energy materials, please read it. I recommend reference 8 and 10 for EQCMD studies. I would like to thank you for allowing me to list some of those sites here.
Thank you, Professor Haga. If you have any question regarding to the lecture, you can contact us. The next webinar, the Professor Saga's 12th lecture, for the moment, we are planning to schedule for June. The detail will be updated in the beginning of next month in the ALS website. For today, thank you and have a nice week.